The curves that we were looking at last time, y equals x cubed divided by 3 and y equals x raised 4. We want to find the volume generated by spinning the enclosed area, and that y equals -2. And many of you grabbed the calculator, graphed it, and nothing. Didn't even help whatsoever. And at the very end of class last time, I showed you that if you want to find the point of intersection, you set the curves equal to each other. Caleb wouldn't believe me, but eventually he joined my side. X would be 1/3. And the point of intersection is 1/3, and if you put it in the calculator, the corresponding value of y (1/81) is approximately 0.013. It is a very small number. There is no way, well, there is a way, but if you don't know how to, you wouldn't even be able to see the enclosed area. So these are problems where the calculator by itself is not going to help. You need to think of it. So you set them equal to each other, solve for x, that gives you the point of intersection. I'm going to show you how to graph this using the calculator. It is not going to be easy, but what should we use to find or get the correct graph? What should we adjust? Thoughts? Go ahead and put the graphs in. I'm going to plug in y equals x cubed over 3 for one curve. The other would be x raised 4. X raised 3, well, I like parentheses, so x raised 3 divided by 3, and the other curve is x raised 4. One, two. There is a point of intersection somewhere right there. You're just not able to see it. We have to zoom it really well. You could do zoom, what is it, 0 or 9? Then 0. Doesn't help much, does it? Does it? No. Clearly, the area on top is not enclosed. This is not the area that we're looking for. The area that we're looking for is right there. Well, forgot to adjust the window. Well, maximum value is going to be 1/3 for x because that is our point of intersection. Why not stop at 1/3? The maximum value of y in this case, well, I have 1/81, that's about 0.013. I'm going to set it at 0.015. Good. Maximum value. Is it helping? He's saying yes, you're saying no. Is it helping? Not helping? It is helping, right? This time I'm pretty much zoomed in, and that's what I have as the enclosed area. You might wonder, what about all of this right there? Well, they are approximately zero. The area between those two curves is negligible. You can just ignore it, but we're not technically ignoring when we integrate it. That is going to be part of the integral. We're just not able to see it. Are you able to see this in your calculator? So that is the enclosed part. Why am I able to see it now after adjusting? There is the point of intersection in the top right side. Bottom part right here is where it kind of blends together. Eventually both curves would approach zero. So that thin strip or that thin enclosed area is what we're going to spin about y equals -2. Good? Were you able to see this in your calculator? Yes? Okay. Placement of the strip is what's going to help you set up your integral in this method, Walsham method. A couple of lectures ago, I actually gave you a hint on how to figure it out. This time it is not the regular axis, rather y equals -2. So what should the strip look like? Is it horizontal or is it vertical, Caleb? Are you asked? Okay, it's vertical. Why? Well, you do the same thing like we would do with x-axis. If you are revolving about the x-axis, we simply put the strip vertically. Here, it is with respect to y equals -2, which is an axis parallel to the x-axis, correct? So here, we will put a strip that way, good? So we have two curves, we have the strip, we just have to find the inner radius, outer radius, and we are done, good? So, for starters, if I draw a strip, say, somewhere here, 0, what is that point for x? 1/3. So I have my bounds of integration, great. 0 to 1, pi 1/3, pi r out squared, outside radius, minus pi r in squared, inside radius, times key part here, is it dx or is it dy? Dx, which is why this strip matters a lot. So dx right there. Only this time the strip goes all the way down there. So inner radius, outer radius. Let's see if we can set it up. Set up the integral. I'll come around and check. Okay. As always, we've got to find the inner and outer radius. I'm going to zoom in terms of the picture so you see things better. It's an arbitrary drawing, just representing that thin strip by stuff over here. And even before you start the problem, you've got to realize that the volume is going to be very small because the area enclosed is very small. I just zoomed in over here. And the axis we are rotating about is right over there, which is y equals -2. Our typical rotation is about the x-axis, but since we have an axis that is parallel to x, we have an additional length. The distance from axis to y equals -2 is 2. Distance, positive. Okay, so So whether it's here or there, same thing. First trick is for the outer radius. We already addressed that this has to be dx, and at this point, you have 2 from here up to the axis, and you're adding a tiny bit. That tiny bit is defined by the curve x cubed, correct? The x cubed over 3 curve is on top, x raised 4 is on the bottom, so x cubed over 3. And as I move this outer curve, it is going to move along x cubed over 3. Agreed? Same logic. The second curve, the inner curve, two plus tiny bit. The tiny bit is defined by the curve y equals 4. Good. So the outer radius is 2 plus whatever that is defined by the function. Pi is in common, so I can pull it out. 2 plus x cubed divided by 3 squared minus 2 plus x raised 4 squared dx. How do we integrate? You have to FOIL first. Don't have to worry about the lower limit, it's all going to be 0, but still. If you FOIL, you'd have 4 plus x raised 6 over 9 plus 4 x cubed over 3. Distribute the negative FOIL at minus 4 plus x raised 8. Sorry, minus x raised 8 minus 4 x raised 4. Those 2 would go away, and if you integrate, you will have x raised 7 over 63 plus x raised 4 over 3 minus x raised 9 over 9 minus 4 x raised 5 over 5. Evaluated between 0 and 1 over 3. That number is going to be very small. Good. You can plug it in at home. Okay, to all that. I just simplified it, you can verify this at home. In case you switch out the inner radius and outer radius, you don't have to freak out. Why? What is the only thing that's going to happen here?
It's just going to be the opposite sign. So
It's just going to be negative, and you just have to think, well, could the volume be negative? No, so just get rid of the negative sign. That's it. So the order, it matters in terms of setup. I might put a question on the exam just to see if you understood the setup properly. So understand the setup, but aside from that, this is the key part. How you evaluate the inner radius, outer radius. Where do we start? Well, you start with our basic principles, fundamentals. If we are going to revolve about x-axis, the strip is dx, which means vertical. And any other line parallel to the x-axis would follow the same strategy. The integral would be in terms of x. If you're going to revolve about the y-axis, strip would be horizontal, and any other axis of revolution parallel to y-axis would follow the same logic. All that would change is the radius. Good? There is a reason why I've repeated it for maybe the 17th time. Because it's the next method that's coming up. It's a little good shot. Good? Yes?
Quick question. With integrate 4x to the third over 3, wouldn't it be x to the fourth or 4?
I got rid of the 2 4s.
Oh, there it is, okay, thank you.
I wrote it in a simplified version. Clear?
Yeah, so it's
Okay, any questions before we move on? No?